All right, buckle in. Number 10. Andrewsarchus, Eocene, Mongolia. A single skull recovered from the Gobi Desert in 1923 measured nearly 3 feet long, with jaws built to crush bone. The skull sat in a crate for months before anyone at the American Museum of Natural History opened it. When they did, the mandible alone stopped the preparator mid-motion. The bone was thick. The zygomatic arches flared wide. The teeth were not designed for grazing. This was not a herbivore. This was something that tore through tissue, and whatever it was eating had no escape route. Andrewsarchus mongoliensis was named for Roy Chapman Andrews, the explorer whose Central Asiatic expeditions carved through the Gobi in the 1920s. The holotype, and to this day the only specimen ever recovered, is a single skull and lower jaw, catalogued as AMNH 20135. No postcranial material, no vertebrae, no limb bones. The entire scientific understanding of this animal rests on one structure, the head. That head measured 83 centimeters in length. The sagittal crest, the ridge along the top of the skull where jaw muscles anchor, was massive, suggesting bite forces far beyond what a comparably sized mammal could generate. The teeth told a clearer story. Large canines, robust premolars and molars built less for grinding and more for shearing. This was a carnivore, or at the very least, a scavenger capable of processing bone. The wear patterns on the molars indicate repeated stress, bone contact, not just flesh. Dating places Andrewsarchus in the Middle to Late Eocene, roughly 41 to 34 million years ago. Mongolia at that time was not the arid steppe it is today. Fossil pollen and sediment data indicate a landscape of floodplains, river channels, and dense coastal vegetation, an environment capable of supporting large-bodied fauna. Whatever Andrewsarchus was, it had prey. Primitive rhinoceroids, early brontotheres, and crocodilian forms all shared the same river systems. The problem is classification. The skull shares traits with Messonychians, an extinct order of carnivorous ungulates, but it also carries features aligned with artiodactyls, the even-toed ungulates that include pigs, hippos, and whales. Some analyses place it within Cetanchodonta, making it a relative of hippos and early cetaceans. Others leave it floating, unresolved, in a taxonomic no-man's land, a hoofed predator, a wolf built on a pig's chassis. The description persists not because it's precise, but because nothing else fits. Every attempt to place it cleanly into a cladogram has failed. Body mass estimates swing wildly. Some reconstructions propose 400 kilograms, others push toward 1,000. Without limb bones, any estimate is an extrapolation from skull dimensions, a method with wide error margins. If the animal was built for pursuit, it was lighter. If it was built for power and ambush, it was heavier. The skull does not resolve the question. It only deepens it. What is certain is that at either end of the range, it would have been one of the largest terrestrial mammalian carnivores to have ever existed. The Eocene was a period of rapid mammalian diversification. Gigantism emerged in multiple lineages independently. Andrewsarchus may have been one of many large carnivores competing for the same resources, or it may have occupied a niche with no parallel. Without a second fossil, the ecological role remains theoretical. The original skull survives. It is still housed at the American Museum of Natural History. No additional material has been recovered in the century since its discovery. The Gobi has been re-explored, resurveyed, re-excavated, but not a single bone from the rest of this animal. The skull remains the only witness, and it is still asking questions. Coming in at number 9. In Ostroncevia, late Permian, Russia. 26 million years before the first dinosaur, the apex predator of Earth's forests carried 6-inch canines and no natural enemies. The skeleton was found in the sandstones of the Dvina River basin, north of Moscow, articulated and nearly complete. The canines measured 15 centimeters, protruding blades that extended well beyond the lower jaw. The skull alone was 60 centimeters long. The animal stood roughly 1 meter at the shoulder. This was not a reptile in the modern sense. This was a synapsid, a member of the lineage that would eventually produce mammals, and it was built to kill. Andrewsarchus lived during the late Permian, approximately 260 to 254 million years ago. It belonged to the Gorgonopsians, a group of predatory therapsids that dominated terrestrial ecosystems before the Permian-Triassic mass extinction erased 90% of all species on Earth. It was the largest of its kind. No other Gorgonopsian reached its size. No other predator in its environment matched it. It weighed an estimated 300 to 400 kilograms, placing it in the same mass range as a modern lion. The canines were the primary weapon, long, laterally compressed, and serrated along the posterior edge. They were not for chewing. They were for puncturing deep, single-strike wounds to the neck or thorax of prey. The lower jaw had a corresponding notch, allowing the mouth to close fully without the canines obstructing the bite. This is a mechanical solution seen later in saber-toothed cats, tens of millions of years after Andrewsarchus disappeared. Convergent evolution, separated by an almost incomprehensible span of time. Its prey likely included large herbivorous therapsids, periasaurs, scutosaurus, and other heavily built animals with thick hides and massive bodies. The Gorgonopsian skeleton suggests speed. The limbs were positioned beneath the body, not splayed to the sides like many earlier tetrapods. This posture allowed more efficient locomotion, a predator that could close distance quickly, then deliver a single decisive bite and wait. The tail was short. The torso was deep. The overall impression was an animal designed for a short, violent engagement, not a prolonged chase. Large-bodied animals competed for resources, but Andrewsarchus sat at the top. No fossil evidence suggests a predator that preyed upon it. Juveniles may have been vulnerable. The closest analog in terms of ecological role is a modern big cat, solitary, territorial, and dependent on ambush. But Andrewsarchus was not a cat. It was not even close to a cat. It was something that occupied the same functional space 260 million years earlier, using a different anatomy to solve the same problem. The Permian-Triassic boundary ended everything. The extinction event, triggered by massive volcanic activity in the Siberian traps, raised global temperatures, acidified the oceans, and collapsed terrestrial food webs. Gorgonopsians did not survive it. Andrewsarchus did not survive it. It vanished along with nearly everything else on Earth. What remains is the fossil record: skulls, postcrania, and those unmistakable canines. Russian paleontologist Vladimir Prokhorovich Amalitsky first described the genus in 1922, naming it after Alexander Andrewsarchus, a geologist. The specimens from the Dvina Basin remain among the most complete Gorgonopsian material ever recovered. They reveal an animal with a heavily ossified skeleton, thickened ribs, and a robust vertebral column, all indicators of mechanical resilience. The question that lingers is not what Andrewsarchus was. The question is what came after it, and why the lineage that produced it never re-emerged. The ecological niche was refilled, but by different organisms with different solutions. The saber-toothed morphology appeared again. The predatory synapsid did not. The body plan was abandoned. The reason for this remains unresolved. Down to number 8, Echolopterus devonian, Germany. A fossilized claw pulled from a German quarry in 2007 suggested its owner measured 2.5 meters, longer than most adult humans. The chelicera was found in a quarry near Wilwerath in the Rhineland region of Germany. A single fossilized claw, a cheliceral finger to be precise, measuring 36 centimeters. From that one fragment, paleontologist Marcus Poschmann and his team extrapolated a total body length between 2.33 and 2.59 meters. The math was straightforward. The implication was not. This was an arthropod, an aquatic arthropod. And it was larger than most humans who would walk the Earth 390 million years later. Echolopterus rhenanii belonged to the Eurypterids, commonly called sea scorpions, though they were neither scorpions nor strictly marine. The group thrived from the Ordovician through the Permian, with the largest species appearing in the Devonian. Echolopterus is the largest of all known eurypterids. It is also the largest known arthropod to have ever lived, terrestrial or aquatic. The title previously belonged to Turrigodus, a close relative. Echolopterus surpassed it. The margin was not small. It exceeded Turrigodus by nearly half a meter in some estimates. The Devonian period, spanning roughly 419 to 359 million years ago, is often called the Age of Fishes. Oceans teemed with armored placoderms, early sharks, and lobe-finned fish. But in the brackish and freshwater environments, estuaries, lagoons, river mouths, eurypterids operated as apex predators. Echolopterus occupied this space. Its chelicerae were not decorative. They were grasping appendages, lined with sharp, curved denticles, structures designed to seize and hold prey. The compound eyes were large, positioned on the top of the head, suggesting a predator that hunted by sight in shallow, well-lit water. The quarry where the claw was found had previously yielded fragments of other eurypterids, along with fossilized fish and plant material. The depositional environment suggests a nearshore habitat, not the open ocean. This distinction matters. Echolopterus may have inhabited environments where water depth fluctuated, where prey was concentrated, where ambush was viable. It did not need to chase. It needed to wait. Fossil preservation supports this interpretation. Body structure can be reconstructed from related eurypterids. A broad, flattened prosoma, the head-thorax region, supported the chelicerae, walking legs, and a pair of enlarged paddles used for swimming. The opisthosoma, the abdomen, was segmented and tapered to a telson, a tail structure that in some eurypterids was flattened into a paddle, in others shaped into a spike. In Echolopterus, it likely served as a rudder. The respiratory system of eurypterids is still debated. Some had gill-like structures on the underside of the opisthosoma. Others may have used a form of primitive book lung. The size of Echolopterus raises questions about oxygen availability. Arthropod body size is constrained by molting, by respiratory efficiency, and by the mechanical limits of an exoskeleton. For Echolopterus to reach 2.5 meters, conditions must have been favorable: sufficient dissolved oxygen in the water, reliable food supply, and minimal predation pressure on adults. All three conditions likely existed in its habitat. The extinction of the giant eurypterids is not well understood. They disappear from the fossil record by the end of the Devonian. Competition with larger fish, changes in ocean chemistry, and the decline of their preferred habitats have all been proposed. None are confirmed. What is confirmed is that nothing like Echolopterus has existed since. The arthropod body plan never again reached this scale in an aquatic environment. The claw from Wilwerath remains the benchmark, a single fragment that redefined the upper limit of what an arthropod could be. The reason is unknown. Number 7. Dunkleosteus, late Devonian, global. 380 million years ago, the ocean's apex predator had no teeth, just self-sharpening bone plates exerting 8,000 pounds of force per square inch. The bite happened in milliseconds. Finite element analysis of Dunkleosteus terrelli's jaw mechanism, published in 2006 by paleontologist Philip Anderson, revealed a bite force of approximately 7,495 newtons at the jaw tip, escalating to over 36,000 newtons at the rear of the jaw. The skull opened and closed in under 60 milliseconds. That is faster than any modern fish of comparable size. The prey did not see it coming. The prey did not have time to react. Dunkleosteus lived during the late Devonian, roughly 382 to 358 million years ago. It was a placoderm, a member of an extinct class of armored fish that dominated marine and freshwater environments for over 60 million years. In Dunkleosteus, these plates formed a rigid shield around the anterior third of the body. The posterior two-thirds were uncovered, likely cartilaginous, leaving no fossil record. Most reconstructions are based on the armored head region alone. The jaws were the defining feature. Dunkleosteus had no teeth in the conventional sense. Instead, the edges of the jaw plates were sharpened into blade-like cusps that self-articulated against each other with every bite, maintaining a cutting edge through use. These bony blades could shear through armored prey, other placoderms, early sharks, anything with a mineralized exoskeleton. Fossil evidence supports this. Placoderm remains have been found with semicircular bite marks matching Dunkleosteus jaw geometry. Some specimens show evidence of regurgitated bone, suggesting the animal consumed and later expelled indigestible fragments. Size estimates place Dunkleosteus between 6 and 10 meters in length, with the largest specimens approaching the lower range of modern great white sharks. It was not the largest fish in the Devonian, but it was the most heavily armed. The combination of speed, force, and cutting geometry gave it an advantage that no other predator in its environment could match. The weight is harder to estimate, but biomechanical models suggest a mass between 1 and 4 metric tons depending on the specimen. This placed it among the heaviest vertebrates of its era. The Devonian Ocean was not empty of competition. Sharks were present. Arthrodires, the order to which Dunkleosteus belongs, were diverse, but Dunkleosteus occupied the apex. Juvenile specimens show different jaw proportions than adults, suggesting a shift in diet as the animal grew from smaller, softer prey to large, armored targets. This ontogenetic shift indicates a predator that adapted its feeding strategy as it aged, expanding its ecological impact across its entire lifespan. No other arthrodire showed this pattern as clearly. The end of the placoderms came at the close of the Devonian. The late Devonian extinction, actually a series of extinction pulses spanning millions of years, eliminated approximately 75% of all species. The causes are debated: ocean anoxia, global cooling, volcanic activity. Whatever the mechanism, the placoderms did not survive. Dunkleosteus did not survive, but their rigid body plan may have been a liability in rapidly changing conditions. The armored body plan that had dominated for 60 million years vanished entirely. The ecological niche was eventually refilled by sharks, by marine reptiles, by mammals, but the specific architecture of Dunkleosteus' bony plates instead of teeth, a skull that functioned as a pair of self-sharpening shears, has never been replicated. The design worked, then it disappeared. Later predators evolved teeth. Later predators evolved jaws. None evolved this. The fossil record preserves the plates, the bite marks, the regurgitated bone. The mechanism that produced them is gone. At number 6. Deinocheirus, Late Cretaceous, Mongolia. For 50 years, all anyone had were 2 arms, each longer than a sedan, and nothing else. The forelimbs were excavated in 1965 during a Polish-Mongolian expedition to the Nemegt Basin. Each arm measured 2.4 meters from shoulder to claw tip. The claws themselves were curved, flattened laterally, and exceeded 20 centimeters in length. The specimen was designated Zpal MGDA/6. Nothing else was found. No skull, no torso, no femur. The arms floated in the taxonomic record with no body to anchor them. For decades, every reconstruction was speculation. Deinocheirus mirificus, the name means unusual horrible hand, was described in 1970 by Halska Osmalska and Uaronewicz. They classified it as a theropod, a bipedal carnivorous dinosaur, but the arms did not match any known theropod. They were too long. The manual phalanges, finger bones, were disproportionately large. The deltopteral crest on the humerus suggested immense musculature at the shoulder joint. Whatever this animal was, it was built to pull, to grasp, to manipulate. It was not built to slash. The gap in the record persisted. Other expeditions returned to the Nemegt. Other fossils were recovered from the same formation, but no additional Deinocheirus material appeared. The arms remained an anomaly, a data point without context. In 2006, a team led by Phil Center published a functional analysis of the forelimbs. They concluded that the arms were not adapted for predation. The range of motion did not support a grasping or slashing function consistent with other large theropods. The claws were too blunt for cutting. The joint mobility suggested a different use, possibly foraging, possibly display, possibly both. The paper reframed the question. Deinonychus was not a predator. But if not a predator, what was it? The answer arrived between 2009 and 2013. Two partial skeletons were recovered from the Nemegt Basin, both poached before being reclaimed by paleontologists. The skulls had been stolen, the bones scattered, but enough remained to reconstruct the body. And the body was unlike anything predicted. Deinonychus was enormous, an ornithomimosaur, the largest known, standing roughly 3.5 meters tall at the hip and weighing an estimated 6 to 7 metric tons. It had a broad, flattened snout duck-like, with a deep lower jaw and hundreds of tiny, peg-like teeth suited for grinding plant matter. The spine bore elongated neural arches, forming a sail or hump along the back. The pelvis was massive. The hind limbs were robust but not built for speed. The stomach contents were preserved in one specimen. They contained fish vertebrae, gastroliths, and plant debris. Deinonychus was an omnivore, a giant, hump-backed, long-armed omnivore foraging in river channels and floodplains. The arms, it turned out, were likely used to reach vegetation, to pull down branches, to gather aquatic plants from shallow water. The claws were hooks, not blades. The Nemegt Formation represents a humid, river-rich environment during the late Cretaceous, approximately 70 million years ago. It supported a diverse fauna: Tarbosaurus, Oviraptorosaurs, hadrosaurs. Deinonychus shared this ecosystem with apex predators. It was not one of them. It occupied a different niche, the largest animal in the environment but not the most dangerous. The original arms from 1965 are still at the Polish Academy of Sciences. The poached and recovered skeletons are in Mongolia. The full picture is now visible, but the decades of uncertainty left a mark. The arms alone misled an entire generation of paleontologists. The question now is not what Deinonychus was, but how many other bodies are hiding behind fragments that do not yet make sense. At number 5. Titanes, Pliocene, North America. A 10-foot flightless bird with a skull the size of a horse's roamed what is now Florida, 5 million years after the dinosaurs fell. The first bone, a tarsometatarsus, was unearthed in 1961 from a gravel pit near the Santa Fe River in Florida. It was identified as belonging to a phorusrhacid, a group of flightless predatory birds that originated in South America. The find was anomalous. Phorusrhacids were not supposed to be in North America. The Isthmus of Panama had not yet formed. The land bridge that would allow faunal exchange between the two continents was still millions of years away. But the bone was there, and it was real. Titanes walleri was formally described in 1963 by Robert Chandler and Pierce Broadcorp. The genus name references the mythological Titans, a deliberate nod to its scale. The species name honors Benjamin Waller, the collector who found the initial specimen. Subsequent excavations at the same site, and at others in Florida and Texas, yielded additional material: vertebrae, pedal phalanges, and fragments of the pelvis. But no complete skeleton has ever been recovered. The skull, the most diagnostic element, remains missing from the fossil record. Phorusrhacids first appeared in the Paleocene, roughly 60 million years ago, and diversified throughout South America during the Cenozoic. They were apex predators on a continent isolated from all other landmasses. The largest species, such as Kelenkin guillermoi, reached heights of 3 meters and carried skulls exceeding 70 centimeters in length. The skull was deep, laterally compressed, and terminated in a hooked beak, a structure biomechanically suited for downward strikes. The beak did not slice. It pulverized. Prey was killed by blunt force trauma to the skull or spine. Titanes was smaller than Kelenkin but still formidable. Height estimates place it between 2.5 and 3 meters. Weight estimates range from 150 to 350 kilograms. The wings were vestigial, reduced to small, rigid structures with a robust clawed digit at the tip. These wings were not for flight. Some researchers have proposed they were used for grasping prey or for display. The function is not settled. The legs were long, heavily muscled, and built for running. Titanes was likely a pursuit predator, not the fastest animal in its environment, but fast enough to overtake the mammals it shared the landscape with. Its presence in North America raises a biogeographic question. The conventional timeline places the formation of the Isthmus of Panama at roughly 3 million years ago, the Great American Biotic Interchange, when species migrated in both directions across the land bridge. But Titanes fossils in Florida have been dated to approximately 5 million years ago. This is 2 million years before the land bridge is thought to have formed. The discrepancy has not been fully resolved. Island hopping, rafting, and earlier temporary land connections have all been proposed. None are confirmed. The extinction of Titanes is similarly unclear. It disappears from the fossil record around 2 million years ago. Climate change, competition with mammalian predators, and habitat shifts have all been suggested as causes, but the evidence is thin. The fossil record for phorusrhacids in North America is sparse, too sparse to establish a reliable population trajectory. What is known is that the lineage that produced Titanes had survived for nearly 60 million years in South America before vanishing entirely. The North American incursion was the final chapter. It ended without explanation. The skull is still out there, somewhere in the sediment of Florida or Texas. Until it is found, the animal's exact proportions, bite mechanics, and feeding behavior remain models built on inference from related species. Number 4. Opabinia, Cambrian, British Columbia. When the first reconstruction was presented at a 1972 geological conference, the audience laughed, then realized the fossil was real. The presentation slide went up. 5 eyes, a long, flexible proboscis ending in a claw, a segmented body with lateral lobes. The room reacted not with awe but with laughter. The reconstruction looked like a joke, a thought experiment, something a graduate student had invented to test the audience. Then Harry Whittington explained that every feature was drawn from actual fossil material recovered from the Burgess Shale. The laughter stopped. Opabinia regalis was described by Charles Doolittle Walcott in 1912 during his initial work on the Burgess Shale deposits in British Columbia, Canada. Walcott had assigned it to the arthropods, a reasonable assumption given the segmented body. But the 1972 reconstruction by Whittington, based on more detailed preparation and examination, revealed that Opabinia did not fit into any known phylum. The 5 eyes, 2 pairs of simple eyes, and a single median eye had no parallel among arthropods. The proboscis, which extended forward from beneath the head and terminated in a grasping structure with spines, was unlike anything in the fossil record. The body bore pairs of lateral lobes used for swimming and a tail fan with 3 blade-like extensions. This was not an arthropod. It was not an annelid. It was not anything. The Burgess Shale dates to the Middle Cambrian, approximately 505 million years ago. The deposit preserves soft-bodied organisms in extraordinary detail, organisms that would normally decompose before fossilization. Opabinia is one of the rarest in the assemblage. Fewer than 30 specimens have been recovered. Most are fragmentary. The best preserved individuals show the proboscis, the eyes, the gut, and the lateral lobes in clear relief. The animal was small, between 4 and 7 centimeters in length, but its anatomy is disproportionate to its size. The complexity is extreme. The proboscis is the most studied feature. It was not a mouth. The mouth was located at the base of the head beneath the proboscis. The proboscis was a feeding structure, flexible, muscled, and capable of reaching into crevices or wrapping around small prey items. The terminal claw could grasp and pull food toward the mouth. The gut contents in some specimens show sediment and organic debris, suggesting Apobinia fed on small particles and organisms in the benthic layer. But the grasping claw also suggests it could capture live prey. Both feeding strategies may have been in use. The 5 eyes represent an unusual configuration. The lateral pairs were likely used for detecting movement and light direction. The median eye, positioned centrally on the head, may have provided forward-focused visual information. This arrangement has no direct modern analog. Trilobites had compound eyes. Some modern arthropods have multiple simple eyes, but 5 eyes arranged in this pattern is unique to Apobinia. The evolutionary pathway that produced it is unknown. The phylogenetic position of Apobinia remains contested. Some analyses place it near the base of the arthropod stem group. Others position it as a member of the extinct group called Apobiniids, with no clear relation to any living phylum. Derek Briggs and Richard Fortey proposed in 1994 that Apobinia might represent a stem group Lobopodian, an early offshoot of the lineage that eventually produced both arthropods and velvet worms. This placement has been challenged. The consensus, if one exists, is that Apobinia sits somewhere in the early radiation of ecdysozoans, the group that includes arthropods, nematodes, and tardigrades, but the precision is low. The animal remains a taxonomic isolate. The Cambrian was a period of extreme morphological experimentation. Body plans emerged that never appeared again. Apobinia is the most visible example, an animal assembled from parts that seem to belong to different organisms. The Burgess Shale preserves it. Nothing else does. It appears in no other deposit, in no other formation. Whether it was restricted to a narrow geographic range or simply failed to fossilize elsewhere is unknown. The record offers a single window, and the window may be incomplete. Number 3. Civathurium, Pleistocene, Africa and Asia. Rock art in the Sahara depicts a creature with a massive body, long legs, and palmate antlers, drawn thousands of years after science says it went extinct. The paintings are on rock walls in the Tassili Enadger Plateau of southern Algeria. They show large, four-legged animals with robust bodies, elongated necks, and branching palmate antlers. The depictions are detailed enough to identify. They are not antelope. They are not cattle. The proportions match Civathurium, an extinct giraffid that, according to the current fossil record, disappeared approximately 8,000 years ago. But some of the Tassili rock art has been dated to between 5,000 and 7,000 years before present. The overlap is narrow. It may not be an overlap at all. It may be evidence that Civathurium survived longer than the fossils suggest. Civathurium giganteum was first described by Hugh Falconer and Proby Thomas Cautley in 1836, based on fossils recovered from the Siwalik Hills of northern India. The name translates roughly to Shiva's beast. It was a giraffid, a member of the same family as modern giraffes and okapi, but it did not resemble either. The body was massive, with estimates placing its weight between 400 and 1,250 kilograms depending on the species. The legs were long but heavily built. The neck was shorter than a giraffe's, thicker, and supported a broad skull with 2 pairs of ossicones, the horn-like structures found on giraffids. The posterior pair was large, branching, and palmate, similar in shape to the antlers of a moose. The anterior pair was smaller, pointed, and positioned above the eyes. Civathurium ranged across Africa and southern Asia during the Pliocene and Pleistocene. Fossils have been recovered from India, Pakistan, Ethiopia, Kenya, South Africa, and Libya. The genus persisted for over 3 million years, a substantial run for a large mammal. It occupied savanna and grassland environments, browsing on vegetation at varying heights. Its dentition suggests a mixed diet: leaves, shrubs, and possibly grasses. The skull architecture indicates strong neck musculature, likely used in combat between males, similar to modern giraffes. The palmate ossicones would have served as both display structures and weapons in territorial disputes. The extinction timeline is where the record frays. The most recent widely accepted Civathurium fossils date to approximately 8,000 years ago, from the Saharan region. This places the animal in the early Holocene, a period when human populations were expanding across the same landscapes. Whether human hunting contributed to Civathurium's extinction is debated. The evidence is circumstantial. Temporal overlap, shared habitat, and the presence of large herbivore remains at archaeological sites. But direct evidence, cut marks on Civathurium bones, for example, is scarce. The tassely rock art complicates the picture. If the depictions are accurate, and if the dating of the art is correct, Civathurium may have survived into the mid-Holocene, possibly as recently as 5,000 years ago. This would extend its known range by 3,000 years. The rock art is not universally accepted as evidence. Some researchers argue the depictions are stylized representations of other animals, antelope, or even mythical creatures. Others point to the specificity of the palmate antlers and the body proportions as too precise to be coincidental. The fossil record for the late survival of Civathurium is thin. No Holocene specimens have been definitively dated to after 8,000 years, but fossil preservation in arid post-Pleistocene environments is poor. The absence of evidence is not conclusive. The rock art remains pigment on stone, drawn by someone who saw the animal or someone who imagined it. The distinction matters. The answer is not yet available. Number 2. Arthropleura, Carboniferous Europe. Tracks preserved in Scottish sandstone show an arthropod over 2 meters wide, dragging itself through swamp, the largest terrestrial invertebrate ever recorded. The trackways were found on the island of Arran, Scotland, and later in formations across Germany and North America. The prints were paired, symmetrical, and deeply impressed into sediment that was once the floor of a carboniferous swamp. Each track set measured over 60 centimeters in width. The animal that made them was not a vertebrate. It was not a crustacean. It was a myriapod, an arthropod related to modern millipedes, and it was the largest terrestrial invertebrate ever to walk on land. Arthropleura lived during the Carboniferous period, approximately 345 to 290 million years ago. The largest species, Arthropleura armata, reached estimated lengths between 1.9 and 2.3 meters, with a body width exceeding 50 centimeters. Each segment bore a pair of legs, over 30 pairs in large individuals. The exoskeleton was mineralized, providing structural support and protection. The body was broad, flattened dorsally, and tapered at both ends, optimized for moving through dense undergrowth. The Carboniferous environment made this scale possible. Atmospheric oxygen levels reached an estimated 30 to 35%, significantly higher than today's 21%. This removed the primary constraint on arthropod body size, respiratory efficiency. Arthropleura likely respired through tracheal tubes, a system that becomes less effective as body size increases. But in the Carboniferous atmosphere, diffusion could support a much larger body. The result was an arthropod reaching lengths no modern millipede approaches. Fossil specimens are rare. The exoskeleton, while mineralized, degraded rapidly after death. The most complete remains come from the Saarland region of Germany and sites in northeastern North America. In 2021, a nearly complete specimen was described from a French quarry, the first three-dimensionally preserved Arthropleura found. It confirmed features previously only inferred: the shape of the head, the arrangement of the eyes, and the structure of the mandibles. Diet has been debated. Early interpretations proposed a predatory lifestyle, a massive millipede consuming other arthropods or even small vertebrates. But the 2021 specimen revealed mandibles adapted for crushing plant material, not seizing prey. Gut contents from other specimens contain lycopsid spores and leaf fragments. The consensus now leans toward herbivory or detritivory. Arthropleura was likely a decomposer, processing the massive volumes of vegetation that Carboniferous swamp ecosystems produced, placing it at the base of the terrestrial food web. The trackways tell a different part of the story. Some show the animal moving across open sediment, not through vegetation, but across exposed surfaces, possibly between feeding sites. The gait was slow, deliberate, rhythmic. There is no evidence of rapid movement. Arthropleura did not chase. It did not need to. In an environment with few terrestrial predators of comparable size, it moved without urgency. Nothing hunted it, nothing could. The extinction of Arthropleura coincides with the collapse of the Carboniferous rainforest biome, an event approximately 305 million years ago that fragmented the vast equatorial forests into isolated patches. As the climate dried and oxygen levels declined, the conditions supporting giant arthropod body plans deteriorated. Arthropleura did not adapt. It disappeared. No descendant lineage approached its scale again. The conditions that produced it, oxygen above 30%, vast swamp forests, no large vertebrate competitors, have never recurred simultaneously. The trackways remain, pressed into stone 300 million years ago by an animal with no modern equivalent. The tracks do not explain why nothing like it has existed since. They only confirm that it did. Number 1, the one you came for. Purosaurus, Miocene, South America. A skull fragment from the Peruvian Amazon belonged to a caiman whose bite force is estimated at 69,000 newtons, the strongest of any known tetrapod. The number came out of the model at 69,000 newtons. The researchers ran it again. The result held. No tetrapod, living or extinct, had ever produced a bite force at this magnitude. Not Tyrannosaurus, not Deinonychus, nothing, and the animal that generated it was a caiman. The fragment that made this calculation possible was recovered from the Pebas Formation in the Peruvian Amazon, a partial rostrum, worn and compressed by millions of years of sediment. When paleontologists scaled it against known caiman skull geometry, the results placed the full animal between 10 and 12.5 meters. The bite force, modeled using regression equations derived from living crocodilians, confirmed what the size implied: the most powerful jaw ever to close on Earth. Purosaurus belonged to the family Alligatoridae, the same group that includes modern caimans and alligators. It lived during the Miocene, approximately 12 to 8 million years ago, in the vast wetland systems that covered what is now the Amazon basin, the Orinoco, and the coastal plains of northern South America. The Pebas Formation and the later Urumaco Formation in Venezuela preserve the remains of an ecosystem unlike anything existing today. A network of lakes, swamps, and river channels stretching across millions of square kilometers, teeming with fish, turtles, birds, and mammals. Purosaurus sat at the top. 3 species are currently recognized. Purosaurus nivensis, the smallest, is known from Miocene deposits in Colombia and Brazil. Purosaurus murandi from the Urumaco Formation reached approximately 10 meters. Purosaurus brasiliensis, the largest, is known from the Solimões Formation in Brazil and is the species to which the 69,000 Newton estimate applies. Its skull is estimated at 1.4 meters. Body mass has been modeled at 5.2 to 8.4 metric tons, comparable to a large bull elephant. The bite force estimate, published in 2015 by a team led by Tito Orellano, was derived using 3 methods: regression of jaw muscle cross-sectional area, finite element analysis of skull biomechanics, and scaling equations from living crocodilian bite data. All 3 converged on values between 59,000 and 69,000 newtons. The mandible was deep, heavily ossified, reinforced with thick cortical bone. The teeth were conical, robust, built for crushing, not slicing. This animal did not merely bite its prey, it collapsed it. Turtles with shell diameters exceeding 40 centimeters have been found in the same formations, some with puncture marks matching Purosaurus dentition. The bite did not pierce the shell, it shattered it. The Miocene wetlands of South America were among the most productive ecosystems in Earth's history. Purosaurus shared its environment with giant river dolphins, massive turtles, and other crocodilians, including the gharial-like Gryposuchus and the broad-snouted Murasuchus. Each occupied a different niche. Gryposuchus hunted fish. Murasuchus filtered small prey from the water. Purosaurus was the crusher, the apex. Nothing else in the system could kill it. The extinction of Purosaurus is tied to the transformation of the South American landscape. During the late Miocene, the Andes continued to rise, altering drainage patterns across the continent. The Pebas Lake system drained. The wetlands contracted. River channels deepened and narrowed. The habitat that supported a 12-meter caiman, shallow, warm, prey-dense water, was disappearing. Purosaurus could not follow the water. It was too dependent on an ecosystem that no longer existed. The legacy of Purosaurus is not just its size. It is the demonstration that crocodilians, given the right conditions, can evolve to a scale rivaling any terrestrial predator. The body plan is not inherently limited. The constraints are ecological, not architectural. Given enough prey, warmth, and water, a crocodilian will grow until something stops it. In the Miocene, nothing stopped Purosaurus. Then the water receded. The bite force record stands. No known tetrapod, fossil or living, has exceeded it, but the Pebas Formation is not fully excavated. The Urumaco is not fully sampled. The Amazon basin holds Miocene deposits that have never been surveyed. The record is incomplete. Something larger may still be buried in sediment, waiting for the rivers to shift and the ground to open. The water receded once. It could recede again.